Good afternoon, everybody. I also would like to start by thanking the organizers of this fantastic conference in fantastic place. So this is the last talk of the session, so it will be kind of general talk, just summarizing what can we expect from quantum simulations. I always start with all these logos of the organization that pay for my research at ICFO and ICREA in Castle de Fels. And because of many logos, I have still a very big group, theory group at ICFO, about 30 people, but I'm slowly reducing it. The outline of the talk is, I'm a professional pessimist, so I will start, of course, with complaining, although I was expecting by the people who are before me that they will only saying the fantastic thing, fantastic, but there were some critical comments in the previous talk, so I'm on the good side. And then I will go to talk about generalities of quantum simulation and give you some examples, mostly from my group, because there is only 20 minutes. So the hype of quantum computing, I mean, has been mentioned already today about the problem that in order to have that we have to find errors and to get a good fault tolerance error correction, we need overhead of 10 to 4 bits, qubits for one logical qubit. We have this problem of scaling with the number of gates, etc., etc. I think I stole this slide from Ignacio already 5 years ago. Okay, a few years ago, we had this wonderful and pioneering experiment of quantum supremacy by John Martinis at Google, because they decided, according to the advice of John Preskill, to try to work with noisy intermediate scale quantum devices. So that was, if I remember, 53 qubit or 51, I don't remember exactly, experiment. In which was explained by John in his talk, so I'm not going to talk very much. This is a random circuit of gates, and then you do the sampling of the state of the qubits at the end, which is proven rigorously to be NP-hard on classical computers, and everything is fine, except that a few years later, matrix product state people from China have come up with the more efficient tensor network programming, which has essentially solved the sycamore problem and became faster. The similar situation is with another sampling problem, which should show for big and small error computers quantum advantage, which is sampling, bosonic sampling in photonic systems. These are experiments of Jaiwei Pan. Here, I don't know the paper that has beaten it, but okay, this is a scheme of the experiment. Simply the bosons go through a random set of beam splitters, and then again at the end you sample what comes out in different modes. But the progress in simulating with tensor networks and other contemporary computational methods of this kind of systems is amazing in the last years. This is one of the very important, actually, product of all these experiments of quantum advantage, that they have stimulated computer scientists and theoretical physicists to work on new code. And really, this is amazing progress in this last years on this thing, which doesn't mean that we have to stop working on quantum computers. We have, because this is fascinating, and obviously we will reach the quantum advantage at some moment. This similar situation has been also mentioned by John, that it's difficult to get really advantage in optimization algorithms. It's also not so easy, or is it really useful to look for it in quantum machine learning? This is a paper by Maria Schult, in which she asks, is quantum advantage a right question for quantum machine learning? And the answer that she gives is no. There is a famous article in, I don't remember what it was in Guardian or whatever, about the hype of quantum computing a year ago or a little ago, maybe the newest one, which, so I would say the first moral is that quantum advantage of NISQ devices so far is for not so useful problem, and they are beaten by tensor network methods. So what can we do in the era of NISQ processors and then the era of computing devices which have errors? And this is another article, I think, from June this year from Matthias Streuer. Maybe he will be talking about it on realistically achieving quantum advantage. So here what he says, I cannot read it because it's right, but roughly speaking is that today's quantum algorithms are not likely to achieve practical speed up. This is in particular true for quantum chemistry applications, for obvious reason that they are not optimal, and optimization problems. Due to limitations of the input and output bandwidth, probably the quantum compute, big compute, will only apply for small data, not big data problems. And essentially, quadratic speedups might not be, like in the Grover algorithm, might not be really of practical importance. So we have to work a lot, but we have to work a lot. This is the moral. But one thing that we can do now are these quantum simulators that was mentioned in the talk of Emmanuel. So what are they? I will again be very general. There exist many interesting quantum phenomena like superconductivity and many others. They have important applications. They are often difficult to be described or understood with the help of standard computers, classical computers. Normally, there are no rigorous proofs that they are NP-hard, or very rarely there are rigorous proofs that they are NP-hard. But every sane physicist believes it is the case. And finally, maybe, so now comes the Feynman idea. Maybe we can use another simpler and better controllable quantum system to simulate, understand, and control this phenomenon. And such system would work as quantum computer of special purpose, and Feynman termed it quantum simulator. So the general, first general comment is that, of course, they can be digital or so that it can make simply great use of existing NISQ devices, like superconducting qubit computers. But they also can be analog, and in most cases, as Emmanuel says, they are analog nowadays. So what are the platforms? There are many which have been mentioned. I have written here a few which are the most important. Superconducting qubits, which have been also mentioned by John. Ultra-cold atoms, discussed by Randy and by Emmanuel. Trapped ions, we didn't have much about trapped ions, but trapped ions are very important also. They have small systems, but very precise and very well controlled. Rydberg atoms, so atoms in the tweezers that interact via Rydberg, excited to high Rydberg states, interacting via dipole-dipole forces. Circuit QED, so these are superconducting qubits, but in cavities. Photonic systems and quantum dot systems in semiconductors, and much, much more. The task and goals nowadays in this kind of physics is to, first of all, simulate fundamental problems of physics, from Fermi-Hubbard model and superconductivity to many others. Then, of course, one would like to do quantum chemistry. We are very far from real competition with real theoretical quantum chemistry done on classical computers, and classical and quantum optimization problems for technology. What will happen in the future? Well, I think that this was also mentioned by Emmanuel, that there will be much more emphasis on properties and things that you can do with quantum simulators. So robustness will be important, scalability will be important, programmability will be important, external access will become to be important, standardization so that we can compare the different results in different laboratories, verification, validation, and certification of their action. One of the things that also was mentioned by Emmanuel is these devices can serve for generation and control on massively quantum correlated states, entangled, and local, and things like that. And of course, now the task and goals will probably change their importance in the next 10 years. Classical and quantum optimization become relevant for technology, will become the most relevant. Quantum chemistry probably on the second place. We will remain on the podium as a physicist, but of course, the public, which is interested in fundamental problems of physics, is much smaller than the other two tasks. So I give you now some examples which are being done in my group in collaborations with colleagues from all over the world. So one of the specialities of our group are dipolar systems. So whatever they are, they can be magnetic dipole atoms, like in experiments of Tillman-Fau. They can be molecules, like in the experiments of Junier. With the electric dipolar moments, there can be Rydberg atoms. There can be Rydberg excited atoms, like in the old paper with Peter Stoller we have proposed many years ago. So many systems. But this particular paper is with Camille Leguin and the group of François Dubin now in Nice, in France. And this is about excitons, which are electron-hole pairs. So obviously they are dipole moments and they interact via dipole-dipole. And what these guys are doing is a situation in which they put on a substrate a set of regularly spaced set of electrodes so that they can create a lattice for these excitons. And this is a square lattice for these excitons. In the half filling, then these excitons are oriented, the dipole moments are oriented perpendicularly to the plane, therefore they repulse each other, and therefore they form a famous checkerboard state, which was apparently for the first time observed in this Nature paper in the experiment. We have done theory for this, which was a Bose-Hubbard model, but you have to be precise. You have to take into account the first excited band, so it's a little more complicated. So on. For a smaller system, you can still do it on classical computer, but if it's bigger, then it's very difficult. So it really, you need a quantum simulation plan, even though it's a bosonic. Another example that I want to show is fundamental system of condensed matter, high energy physics for quantum field theory. So what you can do is what you can propose with quantum simulators, and this is the role of the theorist actually, propose the quantum simulators of some models that you know from exactly high energy physics or condensed matter physics. Here we talk about Schwinger model, which is the model of quantum electrodynamics in one spatial and one temporal dimension, except that we realize it here not like Schwinger with fermionic matter, but rather with two bosonic fields which mimic the fermionic matter. Why is it interesting? Because, of course, the experimentalists who do experiment with cold atoms have a little preference for bosons. Bosons are easier to handle. So, for instance, this kind of system is realized in Laetitia Taruel's lab at ICFO. So we are trying to convince her to go in this direction also. So the model is such that, so what you can study in such model, you can study dynamics. This is the most interesting thing, maybe. Quantum dynamics in these many-body systems. It's very difficult to simulate, but you can do it in the quantum simulator in the lab. So in this case, we have simulated it classically with tensor network states and things like that. But if you go to bigger systems, it's more and more complicated and longer times in particular. So what you do here is you create a meson pair, so a pair of particle-antiparticle. So I have two bosonic fields, the red bosons and blue bosons play a role of particles, antiparticles. This meson, when you let it go, starts to evolve as if it would like to thermalize, but because of the confinement in the theory, it starts to oscillate in time, go back, it's confined and go back. So it doesn't spread, does not thermalize. This is a very nice system to study interplay between the lack and presence of thermalization, between many-body localization, between interplay between the thermalization and quantum, so-called quantum scars, the role of local conservation laws and so on, local conservation laws in lattice gauge theory, which is the Schwinger. And finally, the last example are the, this is a quantum simulator of condensed matter by the condensed matter. So this is the system in which we simulate Hubbard-Holstein model. It's a nanotube, carbon nanotube, which is suspended in two places. And there are 4 quantum dots located on top of it. This is an experiment that Adrian Bachtold from ICFO is trying to realize. Now, in these 4 quantum dots, you can put electrons, so you have Hubbard model essentially, because electrons interact on contact interaction on site, okay, but they also interact via phonons because this carbon nanotube may oscillate, and there are many phonon modes that are possible and that play a role, and there are many phonons that can be created. So in this sense, it's a really many-body system with many particles. And it's becoming quite difficult to classically simulate already with 4 quantum dots, and not even mentioning it would have been bigger. And so you can study the properties of this system. You can study also transport, which we have done in this second paper. So in this case, it's the same system, except that you have left lead and the right lead, so you can study how the transport changes as the properties of the system change. So roughly speaking, my conclusions are that this is a fantastic area, actually, because it's very interdisciplinary. It mixes everything. Condensed matter, quantum optics, high energy, whatever, quantum information, and everything. So it's very enjoyable. And we enjoy it also by combining it with music. So we try to transform the quantum dynamics into sounds. And I will show you the example. So here we write papers on how to do it, but we also have released a long play recently. Now I need the connection, please. Okay, so this is an album that we have released with the music that was presented in the Sonar Festival in 2021. This one is the composition for laptop by Andres Levin Richter, who is a kind of father of Spanish electroacoustic music. He was an assistant of Edgar Varese, so probably French people know very well how important it was. He was one of the grounders of the Princeton Columbia Electronic Music Center, which still exists, and then he founded the center, Phonos Center, which has released this length play together with ICFO, with us. This is, so the sounds are from laptop, and before it would be from tape, but now everybody uses laptop. But there is also percussion by Vasco Tria, who is a free provider.